Alright, in this video we introduce two important quantities for vectors that are norm and scalar product. So let's start. Okay, so suppose we have a vector x in n-dimensional space, x1, x2, and xn. That is an element of this real n-dimensional vector space. Then the norm of x is defined as this. We write like this, and the square root of the sum of squares of these elements, xk squared. Okay, so this is, if we expand, is just x1 squared, x2 squared, and so on up to xn squared. So this represents the magnitude or length of this vector. For example, when this n is 1, when n is equal to 1, then we have just one component for a vector, right? So the norm of this vector is square root of x1 squared. That is actually the same as the absolute value of x1. So in this sense, this norm represents the magnitude or the length of the vector. Okay, so in this case, since there is only one element, we can plot this element on the number line. Suppose x1 is somewhere here, then this absolute value of x represents the distance between the origin and that point. So when x1 is positive, it's just x1. When x1 is negative, then it's negative x1. So it's just the absolute value. And next, in case of two dimensions, when n is equal to 2, a vector is something like this, say x1 and x2. So it's made of two real numbers. So in that case, the norm is square root of x1 squared plus x2 squared. So if we plot this on the plane, then the vector is something like this, and so the source of the arrow is at the origin, and the target of the arrow is this point, x1 and x2. And this norm represents the length of this arrow. Okay? So this can be easily seen from the Pythagorean theorem, because this length is x1 and this length is x2, and this is the right angle. So according to the Pythagorean theorem, x1 squared plus x2 squared is this length squared. So taking the square root, we have this length. So we can do the same thing for n equal to 3, n equal to 4, for in fact for any dimensions, so according to this definition. This norm is in particular called 2 norm or Euclidean norm, because this represents the Euclidean distance from the origin to the point. And this 2 comes from this squared and the square root. Okay, so actually more generally we can define, let's say, p norm. That is something like, let's write like p, and we calculate the absolute value of x1 and take that to the power of p, and x2 absolute value to the power of p, and so on, and xn to the power of p, and take not square root but pth root. Then this is called p norm. And for example, when p is equal to 2, we have this Euclidean norm. And when p is equal to 1, then x1 is, so this is first root is just sum, right? So it's just sum of absolute values. Xn absolute value. So this is the one norm. Okay, using this notion of the Euclidean norm, we define the unit vector to be any vector with the norm of 1. So if the norm of this vector u is equal to 1, then we say u is a unit vector. Unit vector. For example, in the case of 2 dimensions, if we draw the unit circle centered at the origin, so this is the radius is 1, then all the vectors that points to somewhere on this circle, so any of these vectors are unit vectors. Okay, next we define a product between 2 vectors. It's a kind of product, but it's not the product between 2 vectors to produce another vector, but it produces a scalar. So let's say we have 2 vectors, x, and that is x1, x2, and so on up to xn in n dimensions, and y, y1, y2, and so on up to yn. So these are n-dimensional vectors. So for the 2 vectors, their dimensions must be the same. Okay, then we define the scalar product. Or we sometimes call it a dot product or inner product. Inner product. Inner product is defined as, we write like this, angular bracket x comma y, and that is defined as the sum of the product of each corresponding components, so xi times yi. So if we expand this, this is just x1 times y1, this times this, plus x2 times y2, plus, and so on, and xn times yn. So we multiply component-wise, element-wise, then take the sum of all these products. That's called the scalar product between these 2 vectors. Depending on textbooks, there are many different ways to write the scalar product. So in this lecture, we mainly use this one, but sometimes we use x dot y, okay? Or some people might use round brackets or parentheses instead of angular brackets. Or yet some people, especially in physics, might want to use something like this: angular bracket x bar and y and angular bracket close. So all these notations mean the same thing. It's the scalar product or dot product. So dot product, this name comes from this notation because we represent the product by dot. What's important is the result of this scalar product is not a vector, but it's a scalar, okay? So it's a real number in this case, because these 2 vectors belong to a real n-dimensional space. In that case, the dot product becomes a real number. It's a real number, not a vector. So in that sense, the vector space is not closed under the scalar product because the result of the product is not a vector. So the closure condition is not satisfied. Now let's list some of the properties of the scalar product as a lemma. And all these properties can be proved very easily, so you should try it. I will show some of the examples later, but anyway. First, the norm squared norm of a vector is same as the scalar product of the vector with itself. Okay, and second, for any scalar lambda, if we multiply a vector by lambda and take the norm of it, then the result is the absolute value of the scalar times the norm of the vector. Okay, so in that sense, the norm of a product, scalar product, is the product of the scalars. Okay, by the way, the norm is a scalar, right? It's a real number. Okay, let's see. Lambda is a real number and x is a vector. Okay, and 3. The scalar product is commutative, meaning we can swap the order. X times y is equal to y times x. So commutative. And 4, so x, y, z, they are vectors. So x plus y is a vector, and z is another vector. So if we take the scalar product between x plus y and z, then we have the sum of scalar products. Not y, sorry. This should be z and y times z. So scalar product distributes over vector addition. And 5. And same is true for the second component of the scalar product. So x times y plus z is equal to the sum of the scalar products, x times y plus x times z. And 6, the scalar multiplication of a scalar product is equal to scalar product of the vector times the second vector. And so this lambda does not distribute to both of them, but only one of them. Okay, but which one doesn't matter. So this is actually also equal to x times lambda y. Okay, so this lambda can come either here or here. So all these properties are very easy to prove. Just apply the definitions of the norm or the scalar product, and you should try to prove them all. Next, we study a theorem that provides a geometric interpretation of the scalar product. First, we consider the case for 2 dimensions. Okay. For any 2 vectors, u and v in 2 dimensions, the scalar product between them can be written as this. The norm of u and the norm of v times cosine theta, where theta is the angle between these 2 vectors. Between u and v. That is, if we have 2 vectors, u and v, and the angle between them is theta, then their scalar product can be expressed as this. The product of the norm of u, this length, and the norm of v, this length, and the cosine theta, that is cosine of the angle between them. Okay, so let's prove this theorem. First, we consider the case where u and v are unit vectors. Okay, first consider the case where the norms of u and v are both equal to 1. So they are unit vectors. Okay. Then, in that case, as we have seen before, so these vectors are on the unit circle, right? So let's say unit circle centered at the origin. Okay. Let's say this is u and this is v. Okay. And let's say the angle of these vectors from this horizontal axis are, let's say, phi and psi. Let's say this is phi and this is psi. Okay, these angles. And since these two vectors reside on the unit circle, we can write their components as something like this. So since we define this angle as phi, the first component can be written as cosine phi, and the second component sine phi. And v, similarly, can be written as cosine of psi, and sine psi. And if we take the dot product between these two, the scalar product between these two vectors, then we just multiply each component, element-wise product, and take the sum. So cosine phi times cosine psi plus sine phi times sine psi. And using a trigonometric identity, this is, so cosine plus sine is cosine phi minus psi. So if we define, well, by the way, cosine is a even function, so this sign doesn't matter. Plus minus doesn't matter, so it can be also written as psi minus phi. Either way is okay. So anyway, so if we define theta to be phi minus psi, then this is the angle between these two vectors. So this angle is defined to be theta. Okay, the sign doesn't matter. Then that means since we are assuming u and v are unit vectors, this can be written as, so this is actually equal to u norm and v norm times cosine theta. And cosine theta is the angle between these two, right? This is equal to 1, this is equal to 1. So as long as u and v are both unit vectors, then the claim holds. Okay. Next, assume any vector, arbitrary vector. So in case u is not one, u and v are not unit vectors, then we can always write this u as unit, the norm of u times 1 over norm of u. And of course, we are assuming they are not zero vector, okay? In that case, the angle cannot be defined. So we are assuming this is non-zero. The norm is non-zero, and u. So we just multiplied by the norm and divided by the norm. So they cancel to give the same result as this one. And define this as u hat. Okay. U hat is defined to be 1 over the norm times the vector u. Okay, this u hat is actually a unit vector, right? So if we calculate the norm of this, then this is the norm of 1 over norm times u. And of course, this is just a scalar, so we can just take this out. And what's left is just u norm, and they cancel to give 1. And similarly, we can define v in the form of v norm times v hat. Of course, this is v hat is just v divided by the norm of v. Okay, so if we take the scalar product between these two, so these can be written as u norm times u hat and v norm times v hat. Okay, and according to the lemma, let's see, this one, for example. Okay, something is multiplied to this vector, then we can take it out. Okay, so let's first take this scalar out, u, then we have u hat and v norm v hat. Now we can take this scalar out also. Okay, then we have u norm and v norm and u hat times v hat. And since these are unit vectors, we can use the previous result, this result. So this is just norm of u times norm of v times cosine theta, where theta is the angle between these two vectors. And we are done. Now let's look at this result from a different perspective. If you remember how we constructed the set of complex numbers from the set of pairs of real numbers, then if we have a vector u, u1 and u2, then this corresponds to a complex number u1 plus I u2. And suppose these are this is a unit vector, then on the complex plane, this point is somewhere on the unit circle, centered at the origin. Okay. So u1 plus I u2, and let's say the argument is phi. And similarly, consider another unit vector v, v1 and v2. That corresponds to a complex number v1 plus I v2. So the real part is u1, u2, or u1 and the imaginary part is u2 here, and the real part is v1 and the imaginary part is v2. So let's say this is v. So v1 plus I v2, and let's say this argument is psi. Okay. Now consider the scalar product between these two vectors, u and v. Then that is u1 v1 plus u2 v2. Now this quantity is actually the same as, so consider the product between these two complex numbers. Not exactly this one, but complex conjugate of the first one, u1 I u2 times v1 plus I v2. Okay, then this is u1 minus I u2 and v1 plus I v2. And the result is u1 v1 and minus this one and this one. So this becomes u2 v2. So the real part becomes u1 v1 plus u2 v2. So that is that same quantity as this scalar product. And the imaginary part is let's see, I and u1 v2 and minus u2 v1. So you can see the real part is the same as the scalar product, and you should ask then what should this imaginary part correspond to in terms of the product, or maybe another product. That we will see in a later video, hopefully. And also, if we use this polar coordinate, polar form, then this corresponds to e to the power of negative I phi is the complex conjugate of this number, and times I to the power of e to the power of I psi, and that is exponential of I psi minus phi, and this one, in terms of sine and cosine, the real part becomes cosine of this angle, and the imaginary part is sine of this angle. So this psi minus phi is the angle between these two vectors. Okay, let's say it's theta. Okay, then we have this. So cosine theta is the dot product if two vectors are unit vectors. So now we know that at least in two-dimensional space, the scalar product between two vectors is related to the angle between these two vectors. And we can prove the similar theorem for three-dimensional space. And because at least in 3 dimensions, we can still visualize the angle between any two vectors, right? So if you try, you can prove the same thing. But what about even higher dimensional spaces, like 4 dimension, 5 dimension, or 6 dimensions, or even million dimensions? Then do we still have the same result? The answer is not so simple, because in those spaces we cannot visualize this angle between these two vectors. Instead, we actually reverse the argument in the sense that instead of proving this, we use this relation to define the angle. So instead of finding the angle, we define the angle between two vectors by this equation. So how can we do that? Before defining angle by this, but we first consider this equation and change it a little bit. So if this equation holds, then cosine theta should be expressed as the scalar product divided by the product of the norms of these two vectors, right? So for this equation to be true, then this right-hand side should be compatible with the cosine function, okay? The cosine function, the range of the cosine function is between -1 and +1 for any angle theta, right? So that means this right-hand side here should be bounded between -1 and +1, and that we should prove now. And if that's proven, then it's okay to use this quantity to define an angle in terms of cosine function. So now we prove this famous inequality called Cauchy-Schwarz inequality. Schwarz inequality. Okay, so for any vectors in any dimensions, so n-dimensional vectors, we have the absolute value of the scalar product between x and y is less than or equal to the product of their norms. Okay, so this inequality is called the Cauchy-Schwarz inequality. By the way, don't call this as Cauchy. It's Cauchy. It's a French name. So okay, so for all x and y, we have this. So let's prove this. Okay, proof. So in case where either of x and y is 0, or either x is a 0 vector or y is the 0 vector, then this is trivially true, right? Because if x is 0, then this scalar product is 0, and the norm of x is 0, so both sides are 0. And the same for the case where y is 0. So this is true. In particular, the equality holds. So now, we can assume both of them are not 0. Suppose x is non-zero and y is non-zero. Okay, then we have the following inequality. For any real number, lambda, we have x plus lambda y. So norm squared is, of course, is greater than or equal to 0, because the norm is always non-negative. Okay, and if we expand this, first of all, this norm squared is equal to the left-hand side. Left-hand side is equal to, if you remember, as one of the properties of scalar product, this is equal to the scalar product between x plus lambda y with itself. Okay, and you again using the distributive laws and so on of for the scalar product, we have that is so lambda squared and y squared, y norm squared, plus 2 lambda scalar product between x and y, and x norm squared. Okay. So the right-hand side says this is greater than or equal to 0. Okay, but the left-hand side here, this one, is a quadratic polynomial quadratic form of lambda, right? So if you consider this as a function of lambda, then if this is always greater than or equal to 0, so let's plot this as a function of lambda, then this minimum point is greater than or equal to 0, right? So that means the discriminant of this quadratic form should be non-positive. Okay, so that means lambda squared minus, not lambda squared, sorry, this one squared, xy squared minus this one times this one, x squared. So this should be not non-positive. The discriminant should be non-positive. So that means the scalar product between x and y squared is less than or equal to, let's swap the order here, x norm squared times y norm squared. So taking the square root of both sides and just pick the positive ones, then we have the absolute value of the scalar product is less than or equal to the product of the norms of the two vectors. And we are done. Well, so because of this Cauchy-Schwarz inequality, we can say that, so if we divide both sides by this right-hand side, then we have, and so just get rid of this absolute value. Then that means negative 1 less than or equal to the scalar product divided by the product of the norms is less than 1. Okay, so this quantity is always between negative 1 and positive 1. So that means this can be equal to cosine theta for some theta in real number. Actually, it can be between, for example, between 0 and 2 pi. Or it can be in any range, but in any case, there exists some theta angle such that cosine theta is equal to this quantity. Therefore, by this, we can define the angle between two vectors, x and y, for in any dimensional spaces. Okay, next, finally, as an application of the Cauchy-Schwarz inequality, we can prove the generalized triangle inequality. That is, for any vectors in any dimensional space, real space, then we have x plus y, its norm is less than or equal to the sum of the norms of two vectors. Okay, what this means is, so it's called triangle inequality. Okay, because as we have learned before, let's say this is vector x in any dimension, and this is vector y. If we add these two vectors, it's something like, so we move this x, or let's see, so we make the parallelogram. So this y, let's move this source to the target of x, and then move the target of y accordingly. So this has the same length as this, and they are parallel to each other, and this are parallel to each other. And the sum, x plus y, is this vector in the diagonal, this red one. Okay, so x plus y becomes this. Okay, and so this vector is same as y. So the length of this edge is the norm of x, and the length of this edge is the norm of y. And the length of this edge, this edge is the norm of x plus y. So this inequality means the sum of this and this is always greater than or equal to this norm, okay, this length. So this holds for any triangle. So thus, this is called the triangle inequality. And this is actually quite easy to prove. So first consider x plus y norm squared. And of course this is equal to the scalar product of x plus y with itself. So if we expand this, we have x norm squared plus 2 x scalar product x times y plus y norm squared. So just expand everything and use the commutative law of scalar product and so on, and we have this. And using the Cauchy-Schwarz inequality to this part, we have this is less than or equal to x norm squared time plus 2 x norm times y norm plus y norm squared. But these norms are just real numbers, so this is we can factorize this as x norm plus y norm everything squared. Okay, then the norms are positive, so from this and this and this inequality, take the square root of both sides. Then we have x plus y norm is less than or equal to the sum of the norms. And we're done. So by using the norm and the scalar product, we can have more geometric intuition on the properties of vectors. And that's all for this video. See you later.